This is Keith and Brian doing our presentation for the third assignment. So we start off with a second order low pass filter block with our two OTAs, each with their output connected to a capacitor. So at low frequencies these capacitors act as a buffer, and then at high frequencies where they charge really quickly they offer a quick path to ground. Looking at our kind of two nodes of this circuit, the current coming out of the first one here is so proportional to difference in voltages across the terminals, and the rate of change of this voltage because of this capacitor is going to be proportional to that current. Doing the same analysis for the second node, your rate of change of current, rate of change of V out is proportional to the current coming out, which is again proportional to the difference in voltages across the terminals of that OTA there. So yeah, what we see there is at high frequencies the capacitors charge quickly and then offer a path to ground, so this voltage V out here drops. We see the typical kind of low pass behavior where at high frequencies the transfer function drops to 0 and the gain falls away.
So here's the circuit we use for simulation. The first OTA is connected to our ramp, and then the output of that OTA is connected to our second OTA, and then that OTA's output feeds back to its negative terminal and the first OTA's terminal. So we ran our simulation for 3 different sets of bias currents to get 3 different responses to the step. So in the first one we used 2 bias currents, 10 to the -9, taken to the -8, and we got this Q here. And then for our second one we used 1 to the -9 and 1 times 10 to the -9 and then 5 times 10 to the -9, and we got a smaller Q because we used a smaller difference in the 2 currents. And then for the last one we used the same current for both, and we got a very slow response to the step. So here's a frequency response that Caleb was kind enough to do for us on board 17, and from this we can see that the 3 dB frequency occurs at about 26 kilohertz. So we were able to use this information in doing our step responses for the experimental. So our first graph here shows an I bias of 10 times -6, just like the frequency response on the previous page, and we're getting a little bit more than 0.7, but it's still pretty close. For the next one we just doubled the second bias current, and of course our gain's larger. And then for the last experiment we did 40, so we doubled it again, and then the gain is pretty much the same as the step response.
So moving on to the second order C4 OTA device, we now see more of a bandpass type behavior. So again we have this capacitor CL, which connected to the V out, which gives which kind of blocks the high frequencies. So again, when the output signal has a high frequency, there's a path to ground through CL, which reduces V out and reduces your transfer function. When you have a low input signal, a low frequency input signal, there's a big voltage drop across C1, So that means that the intermediate voltage V will be low, and hence the voltage throughout the rest of the device will be low, and you get a low V out. Obviously, in between is when you get the kind of frequency band pass in between those two low regions.
So here's simulation data for the C4, and so we did 3 different runs with 3 different sets of bias currents. So because tau is proportional to the square root of tau 1 times tau 2, where each tau 1 and tau 2 are inversely proportional to their bias currents, if we increase one of the bias currents, we're going to decrease tau. So the larger the product is, the smaller tau's time step is. So as we decrease the bias currents, the time step becomes bigger. So here are the frequency responses that Sitong gave us for the C4 on the chip 17. So as we can see here, you have the bandpass shape, but the gain is only negative 40 dB at the center frequency. So when we actually went and did a step response for the experimental data, we can't actually see anything because I'm pretty sure this equates to like 0.01 gain in the center frequency. So we didn't bother doing a step. Well, we tried doing the step response and then we didn't see anything, so we made this assumption.